Today we're going to look at state space models from transfer functions. So this is a continuation of what we discussed in the last lecture. And in the lecture, we had systems, a mechanical and electrical system, and we derived a state space model based on those. The idea here is to do that directly from the transfer functions if we have them. So it's basically just a continuation of what we did. And the objective, again, is to convert any model or any equation into a simulation diagram or in a state space, which will make it easier to simulate when you use a software like MATLAB or Simulink. So today, we're going to focus on representing different differential equations using matrices. And in particular, I'm going to go from transfer functions directly into state space models. And then create the equivalent simulation diagram for them. So just a review of what we discussed in the last lecture, we started looking at state space models, and we established a standard form for a state space, which is as shown. We have a vector of states that how many elements in that vector will depend on the system order. Typically, if you have a transfer function of second order, that will require 2 first-order equations, third order, 3 first-order equations, and so on. And the standard form for the state space has 2 equations, one that relates the derivative of the states with the states themselves, and the second one that relates the output of the system to the states, x. And in addition, we have a relation established with respect to the input to the system as well. So there are a few steps for analysis that we can follow. This is not a recipe because every time we have a different system, we need to analyze that system specifically. So it's hard to have everything, but here are some steps that we can carry out for analysis. So derive the differential equations, define the state variables, then replace the state variables, the differential equations as a function of the state variables, arrange the equations in the matrix form, and then write both equations based on that. So that's the procedure we followed in the last lecture. And let's do one more example today to just refresh on that. So one key component of this state space model is the choice of the state variables. And we had, I think we introduced a simple approach, which is, do you select the state variables as those where the system can store energy. For example, in a mass spring damper system, if we have a mass, we know that we can store energy in the form of kinetic energy as the mass moves, which means that a good choice for a state variable would be the speed of that mass, v, that will show in the equation sum of forces equals to m times v dot. If we have a rotational system, then instead of the linear speed v, we have a angular speed omega. And then you have sum of torques equals to moment of inertia times omega dot. If you look at an inductor, the inductor can also store energy, but in the form of an electrical field. And that energy, which is a function of the current is in the inductor. 1/2 of Li squared. So I is the current, is the variable of interest where we can store energy through. And the equation for that in the case of an inductor is V1 minus V2 equals to L di dt. Or L or I equals to the integral of V. Okay. In a spring, here just should be K instead of R. And in a spring, you can also store energy in the form of potential energy, which is 1/2 of K times the displacement squared. So the stored energy variable is the displacement, x. And that displacement will show in the equation force equals to K times x2 minus x1. If you now go with a rotational system, instead of angular displacement, the linear displacement, they have angular displacement theta. And we have torque equals to K theta 2 minus theta 1. right? Finally, a capacitor. The capacitor stores energy in the form of a electrical field, and that depends on the voltage across that capacitor. So we can write that the voltage across capacitor is 1/c integral of its current. And the variable of interest will be the voltage V of t. Okay, so nothing really new here, but these are the elements that we can look right away and define them as the state variables that will make the system easier to model. So let's do one example right away. Let's consider this circuit. We have two capacitors, one resistor, one inductor, and a voltage input. Now let's find the state space representation for this particular system. Which variables would you choose to define the state variables based on what we discussed? In this system, we can define more variables, but which ones would you select as the state variables?
Sorry, Prof. I missed what the stored energy state variable was for the capacitor there.
Yes, so for the capacitor, we are talking about an electrical field, so that is the voltage.
Awesome, thank you.
Okay, so here you have two capacitors. We can define one variable V1 as the voltage stored, or the voltage across that capacitor. And let's call here voltage V2, a second voltage across the second capacitor. The output of this system is V0, so it's going to be V2. We have an inductor, and the inductor stores energy in the form of an electrical field, so you can define a current IL going down. And this current is what we can define as the third variable. Okay. So now that we have the state variables, we can define our state vector, and let's define that as V1, IL, and V2. And this will be X1, X2, X3. I can define it in any way, in any order. Let's choose that. What do we do now? Well, now we need to look at the standard form for a state space. X dot equals to AX plus BU. U is the input, in this case, the voltage input. X is the vector, and X dot is its derivative. So now we need to look for equations that will give us the derivative of each of these states over time. That's a good way to approach it. So let's equations to begin with. Where would let's look at a V1, for example. Can you think about any equation that gives directly the derivative of V1? V1, the voltage across here. Are there any equations that will give us the voltage straight away, or that will relate to the derivative of that voltage? That's the current in the inductor, isn't it? Let's call this I1. I1 equals to C times dV1 dt. Okay, so we already have something that is pointing to the derivative of V1. However, I1 is not a state variable. IL is a state variable, and V2 is a state variable. So we need to replace that I1 with something that is a state variable. We have defined here IL going down, I1 here. Maybe you can define I2 over there as the other current. What is the relation between I1, I2, and IL? I1?
Yeah.
I1 equals to I2 plus IL.
Plus IL, very good.
Yeah.
So we could replace this I1 here, but we still have I2 that is not a state variable. We need another equation to find, to describe now I2 as a function of state variables. If you look at the outer loop here, we can do Kirchhoff's law for the outer loop. And what would that look like? Would be VI, the input, equals to V1. Why V1 and not a dV1 over C integral of I1 dt? Because that's not in a state variable. But V1 is in a state variable, so you can just write V1 plus RI2 and plus V2. All right, by following the outer loop here. From this, we can now isolate I2, which is VI minus V1 minus V2, all divided by R. And now this I2 can go right there. And now notice that I1 becomes a function of IL, and a state variable. V1, V2 is state variables, and VI input. So we are good. There's nothing there. And that is an internal variable to the system. So we can rewrite this equation as C dV1 dt equals to I1 is I2 plus IL. So IL plus I2, which is this VI minus V1 minus V2 all over R. Okay. We defined our state variables as V1, IL, V2. So X1, X2, and X3. How can you rewrite this equation now as a function of those? dV1 dt becomes X1 dot, so 1 over C times IL X2 plus VI adds the input, that doesn't change, VI over R, minus V1, that's X1, and minus V2, that's X3. And here we have the first equation for our state space model. That's the derivative of X1, or the derivative of V1 dt. Okay, any questions here?
Sorry, so when we're deciding what's a state variable and what's not, why are we not considering X over the resistor?
X over the resistor.
Yeah, 2 slides ago we had like K multiplied by X2 minus X1.
Yeah.
We're not considering that as a state variable in this case?
Now the resistor only dissipates energy. It doesn't store energy. And so there's no need to create an state equation there. It would be redundant.
Okay, sorry. So what is, oh, that's, never mind. Sorry, that's a spring, not, okay, sorry.
Okay. All right, so now let's look at the second variable, IL, and let's try to derive an equation for IL dot. Can you think about any equation that would give, would have IL dot in it?
Professor, could you just like explain the X equals V1, the matrix there, how you came up with that?
This one?
Yeah.
Yeah, so these are the states that we defined before, V1, IL, and V2. I just arranged them in this order. And we could have arranged them in any other order.
Oh, okay.
So this is X1 is the first element, this is X2, X3, and so on up to Xn.
Right. So
They
they're
have
very
more.
much arbitrary in terms of
They
how
are.
they've been. Okay. As
This
long as you
arrangement
choose
is
those three.
right. This arrangement is
Okay.
arbitrary, but then this element here is always x1. This is always x2. This is always x3.
Okay. Okay. Cool.
Okay, so now let's look at IL. Is there any equation that gives the derivative or that has the derivative of IL in it?
Sorry, before you like start, do you mind explaining like how you got x1 does?
And how I got x1 dot.
Yeah.
So this here is dv1 dt. V1 is x1. Right, so dv1 dt is x1 dot.
Oh,
Okay.
okay. Thank you.
Are there any other questions? All right, so if you look at this element here, dIL dt times L is the voltage across this inductor. So we could write a loop here and write that a loop by saying that a VI equals to this voltage plus that voltage. So that is V1, which is good because that's the state variable, plus L dIL dt. And here we have the derivative of another state. So now how do we write this equation as a function of these variables? dIL dt is x2 dot. And this is equal to 1 over L times VI, the input, minus V1, which is x1. Yeah. We're good here. Any questions?
There's like a couple steps going on there. You just, yeah, but looks good though.
We can rewrite this entire expression as V1 equals to x1 plus L x2 dot. And just factor out x2 dot, isolated for x2 dot, because that's the equation we need for the state space. And so there are two steps here. Okay. All right, so now let's look at the last one. Here is x3, which is V2. How do we are going to look for an equation for that? We need something that gives V2 dot. And what is that? What gives V2 dot? An equation for the capacitor that it gives the I2 V2 dot. That would be
current through capacitor.
Exactly, that would be the current through the capacitor. So I can write that I2 equals to C dV2 dt. And what is I2? Well, we have it here. And you notice that I2, we can leave I2 there because I2 is not a state variable, but all these are, with the exception of the input, but that's fine because it's also part of the state equation. So now replacing I2 with this, we get VI minus V1 minus V2 all over R equals to C dV2 dt. So just move this C over here. And then you have dV2 dt, which is x3 dot dV2, V2 is x3. So dV2 dt is x3 dot. And this is the same as, let's write this again in the state space form, 1 over RC. And moving that there, VI is the input, V1 is X1, and V2 is X3. And that's the third equation we need for the state space representation. Now notice again that all these little manipulations here, they are basic electric circuits. We didn't do anything new. We just need to be smart about establishing these initial equations for the derivative of each state. There's probably more than one solution to this. Also, we could have swapped the order here. But notice that the way we started writing these equations is to look for equations that give the derivative of the one state variable, and then eliminating in that equation any variable that is not a state variable, such as I1 was not a state variable, so we replace that with I2 plus IL. I2 was not a state variable, so we replace that with another equation here that only has state variables here. Right? And you did the same for all three cases. So that would be the main procedure to follow. Now, is there a recipe step by step? No, that unfortunately doesn't exist in engineering. And here we just need to analyze each problem individually. Are there any questions here?
Yeah, so just in terms of our state variables, we are still going to have our input voltage and our output voltage within the state variable equations, correct? Or just the input?
Well, the input and the output, they can be part of the variable, the equations. They have to be part. What we cannot have is our elements that are not the input, and not the state variables.
Right. Yeah, because those
Everything
need to
else.
be represented as state variables so that we can
Correct.
deal with the whole system.
Correct.
Right? Okay.
Yeah. Okay, so let me erase this part, and then I'm going to continue this on the PowerPoint. And then I will erase the rest later when you get to the next exercise. Okay, so now if you move on to this one here, these are the equations we just came up with. All the equations for x1 dot, x2 dot, and x3 dot. And now we can write them in the matrix format. So let's start with the first one. You guys can go ahead and fill out the matrix there. Okay, so let's do it. So now we want to write this in the form of x dot equals to ax plus du, which is the input, in this case, vi of t. So what goes in the first line of matrix A? What goes in the first line of matrix A?
1 over RC1.
1 over RC1, very good. This one here. Second element.
1 over C1.
1 over C1. Third.
Minus 1 over C1.
And that's it. There's no fourth element. The fourth element here is the input. So we'll show in the matrix B as 1 over RC1. Okay. Let me just make this a bit more clear. 1 over C1 minus 1 over RC1. Moving on to the second line, we have x2 dot. So you have only x1, and the coefficient there is negative 1 over L. And then there is no x2, there is no x3 dot, x3. And there is also no input V in the equation for x2, so this element here is 0. And for x3 dot, what do we get? We have at x1, x3, and vi. So x1 is -1 over r c2. x2 is 0, and x3 is -1 over r c2. And then we have the input showing there. Coefficient is 1 over r c2. What
Why
is
are
the
we not
equation?
including 1 over L in the x dot 2 equation
Oh,
in
yeah, we
the
are.
B matrix?
Yeah, we are. Sorry, that's a mistake. So here, that's a good catch. This one here is the equation for x2 dot, and you see there that is, it has indeed vi over L. So that element should be 1 over L. They all have the input, yeah. 1 over L. That's my bad. Okay. What is the equation for the output? The output is V0. What is V0? That's the voltage across the capacitor that we defined as V2, which according to our notation, we define as being X3. So what goes in the matrix for V0 in the output?
0, 0, 1.
0, 0, 1. Very good. And that's the complete state space model for this. Okay.
Sorry, can you explain that V0 part again?
Which one?
V out or V0.
Right. So V0 or V out is the output of the equation. And we need an equation for the output that is given as y equals to dx plus, cx plus du. Cx plus du. So x the states, u the output. Our output is V0, which is the same as V2. They are measured at the same point. According to the notation that we established before, V2 is x3. V2 is x3. So the output of the equation the system is simply x3. Right? The output is simply x3. So if we solve this equation here, we multiply every element of the column vector, the line vector with a column vector, we go back to having v0 equals to x3, which is the same as v2. That's what that equation gives. Okay. Any other questions? Well, if there are no further questions, let's continue. Now let's do something new.
Sorry, Professor, just one V out and 0, 0, 1, and it is x or?
That's x, yeah.
Oh, okay, thank you.
That's the vector x, which is x1, x2, x3. And bold typically means vectors. Okay. All right. So let's move on. If my iPad lets me do that. Okay, now I'm going to skip this representation here, pose the solution. Let's move on to the state space model from transfer functions. So here it's very simple. There isn't really much to talk about. We just have to do an example to see. But here's the formal way to put it. If you have a differential equation written as an equation 1, we have what is the input to the system is on this side here, that's r, and the r times the coefficient b. And you have on the other side of the equation y, that's the output and its derivatives. We have up to order n of derivatives. We can define now n state variables, x1 as being the output itself, x2, the first derivative, x3, the second derivative, up to the nth derivative of that. We will always follow this format. And now we can define the derivatives of each state. If x1 equals to y, then x1 dot is dy dt, which happens to be x2. What is x2 dot? Well, x2 dot is the second derivative of y. Which is the same as x3. What is x3 dot? Well, x3 dot is now the third derivative of y, which will happen to be the same as x4. And we can do that on and on, up to the highest derivative. Because we won't have a, let's say we have a third order system, we can go up to x3 dot, to x triple dot, but you cannot go to x fourth derivative because you have a third order system. So the last equation will always be taken from the differential equation itself. If you want to find the equation for the derivative of the nth state, that will be taken from that equation by solving for the highest derivative here. So you see the derivative of the last state, xn dot, can be now taken from the equation. And everything else will always follow this format. Okay, so let's do one example to make things easier. We'll see that the procedure is always the same. So let's assume that I have this transfer function, and you want to do a state space representation for this transfer function. The first step is to convert this back into time domain. And how are we going to do that? We have a third order transfer function. The input to the function is r of s. The output to the function is c of s. And it's a third order transfer function. We can cross multiply the numerator and the denominator, and we get the equation here. Now, how do we rewrite this equation in the time domain? S to the power of 3 times c of s is the same as c triple dot, isn't it? C of s times s to the power of 3 equals to c of t triple dot in the time domain. What is the second element then? Plus 9s squared times c. What does that become? Plus 9 c times s squared. So this times c becomes 9 times c double dot plus 26 c of t dot plus 24 c of t equals to 24 r of t. Are we good here? Any questions here? No? All right. Now we can define our state variables. You see that the input to the system is r, the output is c. We have a third derivative, so we need 3 states. x1 will be c, x2 will be c dot, and x3 will be c triple dot. Now that we have defined all these variables, we can define their derivatives, and that's where what we just saw comes in. If x1 equals to c, then x1 dot equals to c dot. If x1 equals to c, then x1 dot equals to c dot. which is the same as x2. x2 dot will be c double dot, according to that same thing. But then look at c double dot is in fact x3. So this is actually the same as x3. And now x3 dot is c triple dot, but a c triple dot, that's where the problem comes in. We can define this as x4 because you don't have x4, you only have 3 variables. So this one will have to be taken from the differential equation itself. We're going to use the differential equation here to solve for c triple dot, which is 24r minus 9c double dot of t minus 26c dot of t minus 24c of t. Okay. And now we can rewrite this as a function of the states. How would we rewrite the expression for x3 dot now as a function of all states? x3 dot is equal to what? 24r. Well, r is the input, that doesn't change. 24r of t minus 9 times what is c double dot?
X3.
x3. Very good. Minus 26c dot, which is 26 x2. X2 is c dot minus 24 times c, which is x1. Okay, so that's now the expression for x3 as a function, x3 dot as a function of all outputs. What is the output y? What is y? Y is this side of the y is c of t, is the output is always the right side, left side of that equation. So if y is c of t, y is simply x1.
x1.
Right, simply x1. Okay, so now we have the equation written in state space. So again, the low derivatives just work out, they will work out with the being the next state. So x1 dot will be x2, x2 dot will be x3, x4 dot will be, and so on. Up to the last one. When you get to the highest derivative, we cannot attribute that to another state because we ran out of states. So what we do, we take the equation and you write the equation based on that. It will always fall in this format. Okay, so here are the equations we established, all 3 equations. Now let's write this in the matrix format. We want x1 dot, x2 dot, x3 dot to be written as a matrix A times x1, x2, x3 plus another matrix times the input r of t. So what goes in the matrix A? For x1 dot, we have 0, 1, 0. Right, x1 dot only has x2. For x2 dot, we have only x3, 0, 0, 1. For x3 dot, we have x1 as negative 24, x2 negative 26, and x3 negative 9. And then for the matrix B, we see that r of t doesn't show in x1 dot, doesn't show in x2 dot, only shows in x3 dot. So we have 0, 0, and the respective coefficient 24. And when the equations are written in this standard form, it will always find this sort of matrices where we'll have one element being 1, another element being 0, other elements being 0, and then everything else will be, the last row will always be filled with numbers, and they always fall in this category.
So you're saying that this is a trend for 3 state variable situations?
For
Or
any.
It's always the last one is going to be filled with numbers. Okay.
Yeah.
Cool.
Okay. Let's do the simulation diagram now. If you want to simulate this equation in a simulation diagram, what do we do? We addressed that in the past 2 lectures. How do we start?
Excuse me, Professor.
Yes.
We don't need to write the output one. I mean,
Yeah, let's write the output. It's actually already written here, right? Y is x1, so 1, 0, 0 times x. Let's put it more beautifully. x1, x2, x3 plus 0, 0, 0 r of t. And that comes from this last equation.
thank you.
Okay. All right, so if you want to do the block diagram, what do we do? How do we start for the simulation diagram? Always start from the input. And the input here shows in x3 dot. The input is r, so we can take r of t, multiply that by 24, this element. To that, we can add (24x1) or subtract 24x1. And again, subtract 26x2 and subtract 9x3. These signals, we'll find them later. All we did here is to create this side of the equation. You see each of these elements is coming in. We are adding all of them up, and the result of that operation is this signal here, which is x3 dot, isn't it? Is this clear? This signal is x3 dot. Yeah?
Because there are like 3 subtractions prior to that, it would make sense. Yes.
Yeah.
If you're following
so,
the third equation.
So 1, that, and this. So we are basically adding these 4 elements together.
Oh, but it should be 26 x2.
Yeah.
Yes,
24.
should be 26, yeah. 26. Okay. Now I'll fix this later. That is x3 dot, so this is 26. If that is x3 dot, how do we go from x3 dot to x3? I'll just integrate, and if we integrate, we get x3. Now notice that x3 is the same as x2 dot. So if we integrate this one more time, we get x2 dot, x2. And x2 turns out to be x1 dot. Integrate that one more time, and we have x1. Now we have x1, x2, and x3. We can connect all the signals that are missing there. We know here, for example, we need to multiply x3 by 9. x3 can be taken from there. In the middle row there, we need 26 times x2, and x2 can be taken there. And x1 multiplies by 24. X1 can't be taken from here. And what is the output? Well, the output is y, which is x1. So the output is indeed right there. Y of t is x1. That's the same as the output of the block diagram. And again, this will always follow this format, always. The higher the order, the more feedback loops and the more integrators you have.
Mhm.
But this will always follow the same format. So this is a template for any equation. This is a third order. We have a fifth order, we would have 5 feedback loops, and we would have 5 integrators. But the format is precisely the same, with one restriction. And the restriction is that in our transfer function, we see that here the numerator of the transfer function is not a function of s. What does it mean? It means that the output only depends on the input and does not depend on the derivatives of the input. If we had 24 plus 24s on top, for example, then we would end up with 24 r of s plus 24s r of s when you do the time domain, which is 24 r of t plus 24 r of t dot. Right? So this requires a little more manipulation. We'll see that shortly. But so this template always works, provided that you only have the input and not the derivatives of the input as part of the transfer function. So before we add that portion, are there any questions?
So this is like more of a software kind of like systems and modeling kind of design course, but there would be like an actual hardware representation for this simulation diagram as well, or is this all done in software?
This is all in software. The
Okay.
same way that a model represents the equations analytically, this just helps you simulate that. And as you see in your lab 5, the one that you'll be working on this week, the advantage of this is that you have access to all internal variables, such as the derivatives of all states, which in real life would represent something like speed, acceleration, position, jerk, whatever.
Right.
If you only have the transfer function, you don't have access to these variables. So in a design process, you're often interested in more than just the output. For example, if you have you're working with an insulin pump that delivers a certain, controls something in the body, you want to make sure that the output does what you want, but you also want to make sure that, for example, internally, you don't require 500 volts to operate the pump, or you don't require, or the pump doesn't spin beyond a certain RPM. You can only see these internal variables when you connect different systems by expanding them in the form of block diagrams.
Right. So ultimately this would be like you're basically creating like a digital circuit,
Right.
more so than a analog circuit at this point.
Yeah.
Cool.
So this, we'll see this in lab 5. In lab 5, you have an example where I give you the transfer function and you simulate the output based on that transfer function, and then you're asked to do the same using a block diagram, and then you see that these internal variables will show up and they have access to a lot more information than simply the transfer function. Any other questions here? Can we move on?
Looks good to me.
Okay. All right, so now let's take this one step further. And in this case, now we are going to add the derivatives of the input. This is the same equation we had before. This side of the equation here has not changed. We had that plus B0R. Now we are adding more terms, and these terms are related to the derivative of the input. They are now showing here. Now notice that when you create the transfer function, then this represents now a polynomial in the numerator of the transfer function, indicating that now the output depends on the derivatives of the input. To do this, we're going to proceed exactly in the same way. But first, we need to get rid of the numerator. If you think about this critically, the numerator is just giving you exactly the equation for the output. In the previous one, it would just add a constant on top. In this example here, the output now depends on the derivatives of the input, and which is related to the states. So we can have a second equation to deal with the output. Sorry, a second equation to deal with the output and have the same procedure to relate the internal variables. So that's the objective, is to split this polynomial or this transfer function into two, use what we just did to find the first step, and then add a second polynomial, a second set of state variables to represent the output. So here we're going to introduce a auxiliary variable P of S, and you're going to define P of S as follows. Y of S equals to the numerator of the equation times P of S, always. Which means that if you rearrange, combine this equation there, and replace Y of S with that, we can define P of S as the input divided by the denominator of the transfer function. So always follow this format. You're basically splitting the transfer function into two, one that has the numerator, the other one that has the denominator, and we created this internal variable P of S. Now notice that if you replace P of S in these two equations, we go back to the original transfer function. And you will always define them in this way. So this is another way to see this. These are the same equations. And now when we split them into two, we have what is shown here. Let's look at the first one. If I take the input R of S and divide that by that polynomial, I have P of S. And if I now take P of S and multiply by the top of the equation, I have Y of S. That's from the second equation. And notice that when we combine these two blocks, we have R, Y, and when you combine them, we have numerator divided by the denominator, exactly as in the transfer function. So always proceed in this manner, splitting the transfer function into two with this auxiliary variable P. So now what we can do here is to take this part, and we know how to treat this part. This is exactly what we have before with a numerator that does not depend on the derivatives. And then you can add the second part later on. Okay, so let's see how that plays out. Let's just start with this example. Best way to do this is with an example. We have the space state representation of the same transfer function we had before. If you look at the denominator, or very similar, but now the numerator here has a transfer function on top, a function of S on top. You want to create the simulation diagram for this. So we can start by splitting the transfer function into two, auxiliary variable P of S, write the state equation for the first half as we did before, and then add the second half of the equation later. So let's do that. So here is what you have. Take the transfer function and split that into two. So here it is. Input R. If R is multiplied by 1 over the denominator, we get P. And then when P multiplies by the numerator, we get C. We'll always follow this format. Notice that when we eliminate P, we just multiply the first block and the second block, and then you get the transfer function R to C. Right? Now let's deal with the first portion here and forget about the second. Okay, we can do the same operation we did before. We take the transfer function and we convert that back into time domain. Right, just cross multiply this. S to the power of 3 is triple derivative of P, and so on. So now we converted this into the time domain, and notice that this is now a function of our intermediate variable, auxiliary variable P of T. It's the same thing we did before, but before it was Y of T in the output. Now it's P, because that's not our output. It's just an internal to the system. The output is still to be defined. And now let's define our state variables. And the state variables can be defined exactly as we did before. Before it was y, now it's p. So x1 is p, x2 is p dot, x3 is p double dot. What is x1 dot? Well, x1 dot will be p dot, which is the same as x2. x2 dot is p double dot, which is x3, right, from here. Exactly the same thing we did. Now, what is x3 dot? x3 dot is p double dot. We cannot attribute this to x4 because there is no x4. We have a third order equation. So where we get that from? Well, we get it from here. Do I get it? Can you hear me now? I think my microphones are bad.
Yeah, we can hear you through like probably like a room mic or something, but I don't think it's being picked up by your Bluetooth headphones anymore.
Can you understand me?
Yeah, we can hear you. It just sounds a little echoey.
So what is x3 dot? What is x3?
Is 24 pt minus 9x3 plus 26x2 plus 24x1.
Correct, minus, right? If you are isolating for p3 dot, p3 dot, triple dot here, we have r of t minus 9p double dot minus 26p dot minus 24p. And that reason as a function of the state variables is r of t minus 9p double dot, that's x3, minus 26p dot, that's x2, and minus 24p, which is x1. Yeah? Okay. This is the same thing we did in the last example. So that will relate the states to the intermediate variable, the auxiliary variable p. That's not the output of the system. We still need to deal with the second half of our equation, which is this part here from p to c. C being the output to our system. So now let's do the second half. Well, let's do the first half in matrix form first. x1, x2, and x3. If you want to write that in state form, matrix form, we have x1 dot, x2 dot, x3 dot. And at this point, we know that this is 0, 1, 0, 0, 0, 1, minus 24, minus 26, minus 9, x1, x2, x3, plus 0, 0, 1, r of t. This is exactly the same, or very similar, except that we had 24 here in the last one. Okay, so let me move on to this, which is the second part. Up to this point, it was the same as the last example. Now let's deal with the second part. We have the intermediate variable p of s right there, and we want to now link p of s to c of s. We can write the following expression: c of s equals to p of s times the block. And now we can write the equation in the time domain. So how does c of t look like in the time domain? What is the equation for c of t? Basically taking the inverse Laplace here. What is it? C of t equals to s squared times p of s becomes.
So is this in terms of p? Oh, it is, okay.
Yeah. P double dot of t plus 7 P dot of t plus 2 P of t. Just multiplying out and do the inverse Laplace. Now recall that we defined these variables exactly like this before. We have to keep the same notation to be consistent. x1 equals to p, x2 is p dot, x3 is p double dot. What is c of t? Written as a function of the states.
X3 of t
x3
plus 7 x2 of t
very good.
plus 2x1 of t.
2x1 of t. Excellent. And this is the output y of t. It's the output of the system, that's c of t. Okay, what does that give us? That gives us now a additional equation for the output of our system. And here it is. We simply have that in the state. Let me copy this and paste there. This is y of t equals to that, which we can represent as the following output equation.
Could you just go back to the previous slide for a second?
Yep.
Great, thank you.
Okay, so this is the first equation we got. This deals with the denominator, and now we created another equation for the numerator. This will be the same block diagram for the first part. If you want to relate, take this equation, take this equation here and create a simulation diagram from it. We'll end up exactly what we had before. And this, I'll just give you the result here is, so 24 multiplies x1, so that's here 24, 26, and 9. So this is x3 dot, this is x3, which is x2 dot, this is x2, which is x1 dot, and this is x1. And this is precisely the same thing we did before. Now, there is still one equation missing because earlier this was our output. The output was defined as y of t as one of the states. It was x1. But now it's no longer that. Now the output is this entire equation here, which means that we have to create another equation, add all these elements together to find the output of our system. If you look at the top equation here, the output is given by 7 times x3. So we need to take x3, sorry, not 7 times, 1 times x3. We need to add that to 7x2, which is, sorry, I made a mistake here. Let me start over. I picked the wrong spot. So this is x3 dot, and the equation states that we need x3 times 1, x3 is actually here. And you have 7x2. x2 is right there. And we also want 2x1. And this is now the output of our system. So you see what we did here? We split the problem into two. The block diagram that represents the denominator is precisely the same, that didn't change. We simply added an extra equation to calculate the output of the system. And in this process, we didn't use any derivatives, only integrals. Okay. Does this make sense? Right, so let me recap that one more time. So the first step is to use the equation for the denominator between r and p. And that we know how to do, as the previous example. All we have to do now to move from p to c is to use the second half of the equation And that will simply give us the equation for the output. The first R to P gives the equation relating the internal states and their derivatives, from which we get the bottom diagram here. And the second half gives now the relation between the output and the states that are now readily available in this simulation diagram. So you can just pick them and represent the rest part of the equation for the output, and that's the complete system now. Okay. Are there any questions? These examples are very similar to one another, and so long as you have a transfer function now that falls into one of these two categories, and it will, the procedure is exactly the same. It will just differ depending on how many degrees, depending on the degree of the transfer function.
So for a robotic arm, you're gonna have like up to like how many degrees or how many like, I don't know, how many state variables can you expect with something like that? Up to 4?
It depends on a variety of things. Depends on how many links you have.
Right.
How they are connected. So the more links you have, the more states you will end up with. If you think about one arm, only one link, then you have 2 states, speed and position. So if you keep adding more, and for every link, you'll get 2 additional variables
Per link.
For a 6-stop robot, you can have up to 12.
Nice.
But the problem is it becomes non-linear, because when you calculate the dynamics of that system, it will depend on sine and cosine of angles, and then the system is non-linear, and we can't analyze that with our tools.
With current knowledge in this course. Gotcha.
Okay, are there any other questions? No? Okay, we'll see that with some practice, this will become very easy. It's a recipe for any transfer function. I'm giving you the formal definition here, so you have it, but every time we'll write these equations, the equations will look the same. The block diagram will look the same. There's no mystery. Let's do this exercise here. I'll let you read it, and in the meantime, I'm gonna finish erasing the whiteboard, and then let's do that, and that will be it for today.
So is that like a Fourier series that we can expect to be using for nonlinear systems, or?
No, there are a lot of tools in nonlinear control systems. We can do an approximation around an operating point. We can try to linearize the system. We can even deal with the system as nonlinear. It's just that the analysis becomes quite more complicated.
Okay. Cool.
Okay, so in this model here, we have model for distribution of a drug in the body, divides the process into compartments shown. The rate of change of the amount of a drug in a compartment equates to the input flow rate minus the output flow rate, not show rate. The flow in and out is proportional to the dosage concentration, or as the equation, represent the system in a state space form and draw the corresponding simulation diagram. And the output is a vector that contains each of the amounts xi. Well, we did this before in one lecture, where we had the simulation of the concentration of a drug in the blood. You probably remember that. And all we stated in what all this equation says, is that the flow coming in depends, the volume, the variation in time of drug in each of these compartments depends on the flow coming in minus the flow coming out. And the flow coming in and out will depend on the concentration of drug in one of these compartments. Now let's try to do this one together. Let's write the equations based on the assumption that was just described. So there is a flow rate going between these two, between them, and here we have one in and out. We can write the dosage concentration in x1 dot and then x1. You see that in compartment x1, there is nothing coming in, there is only something coming out. So we can say that x1 dot, or the way it changes over time, is a constant minus k1 times x1. Right? Minus because it's getting out, so the variation of concentration of this drug here is its volume, current volume times a constant, and that goes to x2. Now what is x2 dot? What is the variation of that drug in compartment 2? Is whatever comes in, and what is coming in is what gets out of x1. So that's k1 x1. Yeah. Minus whatever comes out here. Minus k2 x2. Do you remember the example we did about this a few lectures back?
I don't remember, to be honest.
Okay, so this is in one lecture we talked about, we had 2 compartments only, or 3, and we are dealing with concentration of the drug in the blood. Right, so the assumption is from this compartment something is coming out. It's getting in here, something gets out. So whatever is a flow in and a flow out, if you subtract the flow in and flow out, that gives you the variation of the concentration of the drug in that compartment. Right, that's the derivative. Now, what is K1, K2, K3, K5? These are constants. Constants to be determined. We are assuming a linear system. It's simply a proportionality constant. So let's look at the equation for compartment 3. What is the variation of substance X in compartment 3? Because whatever comes in minus whatever comes out. So coming in from X2 is K2 X2. Going out here is K3 X3. Going out here is K4 X3. And coming in from X4 is K5 X4. Are we good? Right, so whatever comes out, remember that whatever comes out here, it goes there. So that's why this flow depends on the volume of X4, not on the volume of X3, because it's going in. This one comes out. This comes out from X3, so it's X3, K4. Okay, what is the equation for X4 dot? X4 dot is just this part here. Right? So what comes in X4 is K4 X3 minus K5 X4. And what is X5 dot?
K3 X5
Is simply K3 X3. Right, it's coming from X3, so it depends on the volume of X3, and there's nothing coming out, the minus 0.
Professor, based on the equations you just wrote, it doesn't seem like the equation in the question, the dxi over dt equation holds.
Yeah, it does for places like here and there. It doesn't to this one because we added this block, right? But if this block wasn't there, then the equation holds for all these top blocks. It just doesn't hold for x3 because we have this one in parallel here. But for the other ones, the equation holds. You see that xk plus 1, xi plus 1. So it's plus the input minus the output. Right? It holds for everything that is in series. It does not hold indeed for x3 because we have the parallel peripheral compartment x4. So yeah, for that one.
So for taking the x2 block, for example, shouldn't the differential equation be ki minus 1 x minus 1 because it's coming from 1, right? Minus ki xi.
For x3, you mean?
X2.
For x2,
yeah,
we have what is coming from this one, so it's x1 k1 minus what is left, what is leaving k2 x2.
Yeah, so x1 is I minus 1, not
Yep.
I plus 1.
Right. Right, that's correct. Is the equation backwards?
The equation says I plus 1.
Yeah, it should be, you're right, the equation should be minus.
Okay, thank you.
Yeah, you're right. I'm gonna fix that. Okay, so here we have all the equations. And again, we went over an example very similar to this in a past lecture. So the logic behind these equations is explained back there in more detail. Is in one of the videos. We can now create a simulation of not a simulation, but a state space model for this. The nice thing is that our variables are already defined. And we can simply write this straight away into state space. And what do we get? Matrix A times X and this system doesn't seem to have any input, so we don't need the rest of the equations here. What makes the system start? Well, it could be an initial condition here. So for x1, only the first one. x2, we have k1 minus k2, 0, 0, 0. x3, 0 minus k3 minus k4 for x3. For x4, we have k5, and for x5, we have 0. For x4 dot, we have x3.
Professor, you put the negative k3 minus k4 in the x2 spot.
There. 0 here. Does that work? Yeah.
Yes.
No, I forgot. Actually, I missed K2. I missed K2 there. Today is not my day. Sorry. K2. Then negative K3, negative K4, then K5, and 0. The next three. X4 dot, we have K4 minus K5 and 0, and then here we have 0, 0, K3, 0, 0. That should be right now. Sorry about that. All right, so I'll just continue this back to this first equation. If you want to do the free body the simulation diagram, we have x1. If you multiply x1 by negative k1, we get x1 dot. And when you take the integral, we have x1. So x1 now can connect back here. For the second one, if you have k1 times x1, so we can take it from there, or from here. K1 multiplied by x1 minus K2 times x2 This should be x2. We'll find it. We get x2 dot. And when you take the integral, we get x2. And we can continue the process on and on. x3, we can have x2 times k2 minus k3 times k3 minus k4 plus k4. Negative sign is up there. This is times x3. This is x2. And that minus or plus k5 x4. All this added together gives x3 dot. Take the integral, we get x3. You can connect there, and now we can go on with the other variables and keep going until we complete the entire block. And you see that this entire simulation diagram will be self-contained. There's no inputs, and all the variables that we needed here, they will come from somewhere when you complete the loop. Okay, so that's it for today. I will give 2 exercises or 3 for you to try. This one, very similar to what we did, and this one again with the top of the equation having an extra portion, and then next lecture we're going to move on to time response. Now we're going to analyze how the systems respond to certain inputs. Okay, but that's enough for today. I'm 10 minutes late again, so thank you everybody, and we'll see you again on Thursday. I should be able to post the assignment soon, and if you have any questions, then come see me during office hours. I'll be available there for 1 hour or 2 hours a day, starting in 5 minutes. Okay.